Now we're going to talk about using energy again. And I want to talk about heat engines and heat pumps, but we're going to get into basically a philosophical question and say, like, what's the deal with thermal energy? I have here a power plant, and power plants typically run with an efficiency that's something like 30% to 50%, and that's shockingly low, but there's a reason for it, and that reason is something we'll talk about. Now I want to talk about different limitations to efficiency. Okay, when you're moving on level ground, you're not getting anything for your energy output. It costs you a certain amount of energy to move. That is basically a process limitation. That's just as a function of how you are put together. Kangaroos, if they go 10 kilometers, they use about half the energy that you take to go that distance, that you take to run that distance. Kangaroos are just more efficient than you, and it has to do with the fact that they've got energy return mechanisms in their legs. They've got stretchy tendons. So you can design there are creatures on the earth that have very, very efficient means of locomotion. Just because they have different kinds of body plans. But there's some fundamental limitations. So this power plant right here is about 40% efficient. And here's the thing, no power plant in the world does very much better than this. And that is a fundamental limitation of how the world works. I mean, and you just can't do better. People would do better if they could, because if you could take your 40% efficient plant, you could make it 50% efficient. For every joule of energy input from fuel of some kind, you would get more output. So people would do it if they could, but they can't. And it all has to do with this idea of thermal energy. And thermal energy is the kinetic energy of atoms and molecules. So I'm imagining here the clearest case of this is an ideal gas. So I have a helium balloon, and inside there I have these the atoms, and they're moving around at really, really high speeds. This kinetic energy of the helium atoms is the thermal energy of the balloon. The thermal energy is the total kinetic energy. And as we'll talk about, and this will be important to us in chapter 12, temperature is the average kinetic energy. Okay? So if the temperature outside is 20 degrees Celsius, that's the measure of the average kinetic energy of atoms in the air. The total kinetic energy is the thermal energy. Now let's take our basic energy model and we're going to expand it. So we have the idea of a system, and then everything else in the universe is the environment. And if we consider situations where the kinetic energy is not changing, the potential energy is not changing, our basic equation reduces to this. The change in thermal energy of the system is equal to the work plus the heat. And the work is positive if energy is coming in, it's negative if it's going out. The heat is positive if energy is coming in, it's negative if it's going out. And if I put in heat or I put in work, I can change the thermal energy of a system. And if I want to reduce the thermal energy of a system, I have to take energy out by having the system do work, or else I have to take heat out. That is the first law of thermodynamics, but it's not really a new law of physics. This is basically just conservation of energy in kind of a different guise in situations where we're just considering work and heat, but we're not considering changes of kinetic and potential energy. And that's the kind of thing we're going to consider right now. Now, thermal energy is really central to our story right now, so we need to talk in a little bit more detail about thermal energy. I want to consider two different cases. First off, let's consider a cold baseball tossed at a high speed. All the atoms, all the molecules are moving in the same direction at a high speed. Okay, that is very, very orderly, or we would say low entropy. On the other hand, if you look at a hot gas inside a helium balloon, so I look at a hot balloon, the molecules are moving really, really high speeds, but they're moving in random directions. This is a situation of very, very high entropy. Okay, and so if I look at the difference between these two cases, and it turns out if you have a baseball thrown at cold baseball thrown at like fastball pitch speeds, the amount of energy is comparable, the amount of kinetic energy is comparable to the total kinetic energy of all the atoms inside a helium balloon. So these two kinetic energies are about the same, but the top one is very, very orderly. The bottom one is very, very disorderly. The top one is low entropy. The bottom one is high entropy. And so when I have thermal energy, it's associated with higher entropy because the motions are random. And we can define entropy that way. It's like a lack of order or a randomness. We'll have more things to say about that later. And the second law of thermodynamics, which is a new law of physics, says the entropy of the universe always increases. Now let's think about what that means. We said that if I have kinetic energy, that's low entropy, and if I have thermal energy, that's high entropy. So if I have something moving and has a certain kinetic energy, and it slows down and stops, and the kinetic energy turns into thermal energy, that increased the entropy of the universe. That will happen spontaneously. If you drop something, it'll fall to the ground, it'll bounce for a while, it'll slow down and stop. All of the kinetic energy has turned into thermal energy. But it won't go back the other way. You won't have a warm patch of floor and you're going to put a ball on it and it fires the ball into the air. That wouldn't violate the conservation of energy, but it would violate the second law of thermodynamics. So basically, when you turn energy into thermal energy, it's a one-way trip. It's very difficult to get the energy turned backwards. Or to get the energy to turn from thermal energy into another form. And that's problematic because if you look at power plants, power plants are heat engines. They're basically taking the energy that you get from burning some sort of fuel or from a nuclear reactor, and they take that thermal energy and you convert that into electric energy or some other sort of useful work. And when you do that, you can't do it with 100% efficiency. So heat engines have limited efficiency, and the thing that limits them is this second law of thermodynamics. So you pull in heat from a hot reservoir, so run a heat engine, you dump heat into a cold reservoir, you extract some of that energy as useful work, but you can't get 100% as useful work. Okay, you just can't do that. You have to dump some of the heat into a cold reservoir, and that is a fundamental limitation of the universe, and it's the second law of thermodynamics. So this idea limits the efficiency of heat engines. And I'll tell you, you already have one heat engine in your life, and that's the engine under the hood of your car. The engine under your car is a heat engine. You burn gasoline, and what you do is you end up with a lot of thermal energy. And then you end up with a lot of thermal energy in one place in the hot gases. You're going to use that to do some useful work to make your car move forward and to run the lights and the radio and all that. But you're also going to dump a significant amount of heat in the environment. You're going to dump it into a cold reservoir, a place that is colder than the hot gases, which is pretty much everywhere. And you just dump it out the radiator in the front of your car. You are dumping heat into that cold reservoir, and you have to do that. And the amount that you have to dump is specified by the second law of thermodynamics. Now, generally, the efficiency for a heat engine is what you get divided by what you had to pay, and what you get is the useful work output. And you divide that by what you had to pay, which is the thermal energy of the hot gases or whatever your heat engine is using. That's how we define it, and it's equal to the maximum possible efficiency that you can get is this number right here. It's 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. And there are practical limits on how cold you can make the cold reservoir and how hot you can make the hot reservoir. And so that limits the possible efficiency that you can get. Now let's take a look at a practical problem. And this is a problem having to do with the nuclear power plant. It just have numbers for a specific power plant. So in each second, nuclear reactions in the core generate 2,000 megajoules of thermal energy. And that's used to boil water and create high temperature steam at 300 degrees Celsius. The steam makes a turbine, making 700 megajoules of electric power. The steam is condensed and cooled to 30 degrees Celsius, and then the cycle starts again. So the two questions we have to ask are, one, what is the maximum possible efficiency of the plant? And two, what is the plant's actual efficiency? And then the third question, how much energy is deposited in the environment every second? Let's take a look at these in turn. And I'm going to solve this problem the way that we do. First off, I'm going to strategize. And my strategize step is to say this. A nuclear power plant is a heat engine. Okay, it's a heat engine. And the second thing I'm going to do is I'm going to prepare. And to prepare, I'm going to draw a picture of the heat engine and draw the energy inputs and the outputs. And that looks something like this. So here's my heat engine, here's like my steam turbine, and what's coming into the steam turbine is a certain amount of heat, 2,000 megajoules of heat every second come in, and they're coming in at a temperature of 300 degrees Celsius. And then we're dumping some of that energy into the environment, And this number that comes in, I'm going to call QH. That's the amount of energy that comes in the hot reservoir. The amount that gets dumped in the cold reservoir, I'm going to call QC. And it's dumped at a temperature of 30 degrees Celsius. That's the temperature of the cold reservoir. Okay? And then also we get some energy out. Okay, get some energy out. We're going to call that W. That's my useful work output of the plant. And we know what that is. That is 700 megajoules. Okay, so that's my preparation step. I've helped basically wrap my mind around the problem. And then let's do some solutions. Let's do some solving. Okay? And first piece, I'm going to calculate the actual efficiency. Well, the efficiency actual is what you get divided by what you had to pay. And what I get is 700 megajoules of electric power. What I had to pay was the heat input from the nuclear reactions, because when the nuclear fuel runs out, I've got to get more. So my actual efficiency was 700 megajoules of useful work out. That's what I get, divided by what I had to pay, which was 2,000 megajoules. And so my efficiency is 0.35 or 35%. The plant is actually 35% efficiency. Now you could do better. And the maximum efficiency of any heat engine is just equal to 1 minus Tc over Th. And the temperatures that appear in there have to be Kelvin temperatures. And so the temperature of the hot reservoir, okay, is going to be 573 Kelvin. The temperature of the cold reservoir is going to be 303 Kelvin. So if I calculate the maximum efficiency, okay, the maximum that I can possibly get, we get 0.47. So the actual efficiency is 0.35. And you might think, well, 35% efficient, that's pretty terrible. Nature limits us to an efficiency of no more than 0.47. So it's actually fairly close to the maximum possible efficiency. They're not doing too bad. But here's another thing I want to think about. You're pulling in 2,000 megajoules every second. You're taking 700 megajoules and turning it into electric energy. What's left over is an additional 1,300 megajoules. And that energy is just deposited in the environment. And so one of the big things with power plants is not only the pollution that they create for things that they send up their stack, but also thermal pollution. I'm taking that energy and I'm dumping that in the environment. And so I have 1,300 megajoules, which is deposited in the environment every second. And here's my assessment. These numbers are actually realistic in terms of the numbers that I saw for this actual plant. And for this actual plant, a really, really interesting thing was they had a lot of, I visited there, they had a lot of manatees there. And the manatees are hanging out in the warm water that is produced in the outflow from the power plant. And it's a nuclear power plant, so it's got really, really intense security. So these manatees have warm water in a very, very tightly controlled and tightly patrolled environment. There's no power boats in there. The manatees are living their best life at the power plant. And it turns out power plants in Florida have custody of a lot of the state's manatees, which is kind of cool. And now we want to look at another device called a heat pump. Now that sounds really abstract and kind of weird, but think about this. The inside of your refrigerator is cold. The outside of your refrigerator is warm. And so heat is going to naturally flow from the outside of your refrigerator to the inside of your refrigerator. And if nothing was done, the inside of your refrigerator would become the same temperature as the outside, and your refrigerator would basically not be doing anything for you. So what you need to do is you have to take that heat and you have to pump it back into the room. But when you do that, you're pumping it basically uphill in the temperature sense. You're pushing it someplace it doesn't want to go. And doing that requires energy. So if I take heat and I pump it out of a cold reservoir and pump it into a hot reservoir, I'm making it go against the direction it wants to go. That requires a certain amount of energy input. And we can define the efficiency, which for heat pumps we call a coefficient of performance, this way. It's what you get divided by what you had to pay, and what you get is the cooling. How much energy did you suck out of the cold reservoir? What you had to pay was how much work did you have to do to perform the transfer. So QC divided by the work input. And the maximum possible coefficient of performance, which is basically an efficiency you can get, is related to the temperatures of the hot and the cold reservoirs thusly. Now, another type of heat pump you can have is an air conditioner, and your air conditioner keeps the inside of your house cool when the outside is warm. And heat would naturally flow from the warm outside to the cool inside. And so you've got to take that heat and you have to pump it back out. So let's calculate, okay? If the temperature inside your house is 20 degrees Celsius, and the temperature outside is 35 degrees Celsius, a typical air conditioner is going to move 5 joules out of your house at a cost of 1 joule of electric energy. So we can compute the actual coefficient of performance and the maximum coefficient of performance, given this expression right here for the maximum possible coefficient of performance. And let's do that. So first off, let's compute the actual. Well, coefficient of performance is an efficiency. It's basically what you get divided by what you had to pay. And what you get is 5 joules of cooling. You pumped out 5 joules of heat, and what it cost you was only 1 joule of electric energy. The coefficient of performance is 5. That's 500% efficient, really. You're pumping 5 times as much heat as you're putting in energy, which is kind of amazing. It's kind of amazing, but it's less amazing if you consider how good it could be, because the maximum possible coefficient of performance is given by this expression, Tc over Th minus Tc. And those expressions have to be in Kelvin. You have to take those and put them in Kelvin. And if you do that and you actually calculate what the maximum possible coefficient of performance is, what you get to 2 significant figures is 20. So that coefficient of performance of 5 sounds really good, except when you realize it could be 20. And if we're looking at places as a society where we can minimize energy use, one is we could look at our air conditioning. You can also insulate your houses better too, so that you're going to have to pump out less heat. So there's a lot of things that can be done in terms of the way we heat and cool our dwellings. Now here's something I want you to think about. You're taking the heat and you're pumping it out. If you have an air conditioner inside your house, outside your house, you have to have some sort of a unit that is dumping the heat into the environment, and you can find that someplace. Now we've been talking a lot today about thermal energy, and thermal energy is sort of special, and we want to look at what happens to systems when you add or subtract thermal energy. That's a little bit more having to do with thermal properties of matter. That's the subject we'll take up in the next set of slides.